All right, the next thing we're going to go over is how do we measure um, radiation using half-life. I know you heard of half-life before. And half-life is more used when you talk about you're being exposed to a radioactive substance. How long will it take until the radiation has diminished to a safe level? And we talk about half-life because it means how long will it take for half of that substance to decay into something else. My example is going to be iodine 131. And if I start with 20 grams of it, after one half-life would go by, I would have 10 grams of it left. But now that the other 10 grams would become a different element. So you see that the iodine 131 has become a xenon 131. No change in mass. So what's happened is that the iodine 131 has released a beta particle when it did this. How much of iodine 131 will be left after another half-life? Only 5 grams of it. So you notice that we're cutting the amount in half each time a half-life goes by. And after 3 half-lives, only 2.5 grams of iodine 131 will be left. So 3 half-lives means an eighth is left. 2 half-lives means a fourth is left. 1 half-life going by means a half is left. Now here's a chart showing you how it diminishes graphically over time. This is the same one from the previous example, iodine 131. See how we kind of get a curve like that. And they give you the time elapsed. So if this one is 8 days is 1 half-life, 16 days is 2 half-lives, 24 days is 3 half-lives. So to determine that it would be 3 half-lives, we'll take the 24 days and divide it by 8. And that gives us the 3. Here are some half-lives of particular isotopes. We have carbon-14, 5,730 years. Carbon-14 is used to date objects that were made from plants. We have potassium-40, over 1 billion years. Radon, radium-226, 1,600 years. Uranium-238, 4.5 billion years. The half-life tells us how much radiation is being produced every second by a particular sample. The shorter the half-life, the more radiation is being produced, and the faster that sample is undergoing decay. So uranium-238 has been around a long time and will continue to be. Now you notice some medical isotopes, we have very short half-lives. Now we don't want these substances hanging around in the body, so they decay quickly. Now you might wonder then, does that mean that they're more dangerous? Well, you use such a small amount of them, and none of these will decay by releasing alpha particles, because that would be deadly. So they all decay by releasing either beta particles or gamma rays. Now we have a couple of formulas that you want to jot down. The first one is, how do you calculate the number of half-lives? We take the time period and we divide it by the half-life. I showed you that in the previous slide. We did 24 days was the time period, dividing by 8 days gave us 3 half-lives. And the other formula we have is, if we want to know how much will remain, the amount remaining after a certain time frame, we're going to take our original amount and multiply it by 1/2 raised to the power of the number of half-lives. So 1/2 to the first is just 1/2. 1/2 to the second is a fourth. 1/2 to the third is an eighth, etc. So let's take a look at a problem we can use those formulas. A nuclear reactor produces iodine 131, which has a half-life of 8 days. If the reactor initially contained 100 grams of iodine 131, how much remains after 32 days? So how many half-lives went by? So we're going to use our half-life equation that I had in the previous slide. So number of half-lives then will equal the time period, in this case is 32 days, divided by 8 days, which is the half-life. So 4 half-lives went by. How much will remain? Now we're going to use our second formula. So I take my original amount, which is my 100 grams, and I'm going to multiply that by 1/2, where the 2 is raised to the 4th power. And I get 6.25 grams. Now 1/2 to the 4th really means 1/2 times itself 4 times. So that's going to be 1/16. Now, here's a little bit on radiocarbon dating since it's always in the news. Where does the carbon-14 come from? So if you follow along here, the first step, cosmic rays enter the Earth atmosphere, and they collide with atoms, creating so that neutron is the nitrogen-14 atom, and we get carbon-14 produced and a proton. Now the plants absorb carbon-14 combined with oxygen to give them radioactive carbon dioxide. And that carbon dioxide will be used to make sugars. So plants like that have a particular amount of carbon-14 in them all the time. The ratio between carbon-14 and stable carbon-12 then pretty much stays the same as long as the plant is alive. So the fourth step, animals and people eat the plants and take in carbon-14, so we have some in us. And then, following the death and burial, wood and bones lose carbon-14 as it changes to nitrogen-14 by beta decay. So the carbon-14 to carbon-12 ratio diminishes with time. So when they dig up an old axe handle or something like that, and they measure the ratio between carbon-14 and carbon-12, that tells them how many half-lives go by and allows us then to calculate how old the object is. So you notice, interestingly enough, you start with nitrogen-14 way up here, and at the very end, wind up making nitrogen-14 again. Medical applications. Radioisotopes with short half-lives are used in nuclear medicine because they have the same chemistry in the body as non-radioactive atoms. In the organs of the body, they give off radiation that exposes a photographic plate, giving an image of the organ. Now, an MRI doesn't do that, but the other kind of scans do. So here's one here where a person is having a scan of their thyroid gland. Here are the two lobes of the thyroid gland. And in order to see what's in here, this person has taken in some radioactive iodine-131. And we can see the energy that's being produced from that. Here's a CT scan showing a brain tumor right here. Here's a PET scan, which stands for positron emission tomography of a normal brain versus an Alzheimer's patient's brain. Now, the blue indicates areas where nothing much is happening. You notice it's a lot more in the Alzheimer's patient than in the normal brain. Here's our MRI scan of the heart and lungs, with the left ventricle shown in red. So where the lungs are these black areas here, because remember, a lung is mostly a bag with just gas in it. Okay, nuclear fission is a process where an unstable or radioactive nucleus will split just about in half and produce 3 fast-moving neutrons and a lot of energy. Very few isotopes fission. There's only a few of them. And those that do actually provide the power for atomic bombs in nuclear reactors. So again, we have one atom splitting in half pretty much, and then we get a lot of energy released, and we get 3 more neutrons, each of which could make another uranium-235 atom split. And eventually we have so many splitting at once, we have an atomic explosion. So one way to slow the reaction down is to absorb these neutrons. And that's what happens in a nuclear power plant. Now, an atom bomb, you just let it go crazy until finally you reach that critical mass where so many are decaying at the same moment, you have an explosion. So here's a nuclear power plant. Now, the reactor is here. We have control rods which can absorb the neutrons that are being produced and slow the reaction down. And then we have fuel rods in here. So there's a lot of energy released from fission, and that energy is picked up by this refrigerant here, and that refrigerant gets very, very hot, and that's put into this transferring vessel where it heats water up. The water changes to steam, and then the steam turns a turbine and makes electricity. And then that steam is condensed. That's why we have to have this near body of water. The steam is cooled back down, where it can then, re-enter. They have it come back, re-enter the containment vessel here and pick up more heat. Now you notice that whatever fluid is in here coming from the reactor, that never leaves that. So you must have to cool that down before it can be pumped back in. Now the nuclear accidents that we have on this planet have always involved a little valve down here where, for different reasons, the coolant has not been pumped back into the reactor, and the control rods have stayed out, and so the reactor goes crazy, and so much heat is produced you wind up with an explosion. Now, that kind of explosion is not going to be an atom bomb. There's not enough radioactive material to produce an atom bomb in here. Like it happened in Fukushima in Japan a few years ago. This is what happened here. They lost the coolant that will pick up that heat. Because there's no way to stop this from reacting. So this is pretty much how a nuclear power plant works. Now, the other reaction we're going to look at, and the last one, is on fusion. Nuclear fusion, which is the energy that powers the universe, really. So it's what happens that powers the sun. In order to have fusion occur, you have to have very high temperatures. You can see here, 1,000,000 degrees centigrade. We're going to combine small nuclei into larger ones. The small nuclei are really hydrogen nuclei. You get a tremendous amount of energy released, and we don't get any radioactive waste, which is great. So this occurs continuously in the sun and the stars. Now here's an example of it here. Now in this case, we have two radioactive isotopes of hydrogen. This one is called tritium with an atomic mass of 3, and this is deuterium with an atomic mass of 2. Now there's so much energy and pressure on the sun that they can be forced to combine together, and they wind up making helium, and we get a neutron produced. Now I want you to notice, you see the mass at the top is 4 and 0. That's just 4, yet we started with a mass of 5. Here we have total mass of 2, here we have total mass of 3. Something seems to be off. Well, remember that the one down here, the neutron, this one should really be up here. So I want to correct that for you. Yeah, a neutron is really a mass of 1, cross that out, mass of 1 and a charge of 0. So this slide has to be corrected in that respect. Now there is a little bit of a change of mass into energy. We get the energy produced here. So fusion reactors have been produced, but they haven't been feasible yet. It takes as much energy to get out of these fusion reactors as it takes to make them work. Eventually, hopefully, this will happen. Okay, and that's going to be it for our chapter on nuclear radiation.